Today for this lesson, we're going to be talking about continuity and the intermediate value theorem. I can find constants to form continuous functions and use the intermediate value theorem to find a value c. Before we get there, let's go ahead and take a look at the warm-up. The first question says to state the domain. As soon as I see a square root, I'm thinking to myself, I'm going to have a problem if I have a negative number underneath that square root. Right? If there's a negative number under a square root, then there would be no real solutions. So I want to exclude any value that would give me a negative under the square root. In other words, 2x minus 3 would have to be greater than or equal to 0. Right? Because we can take the square root of 0. That's fine. Where we want to run into problems is if it's less than 0. Like that would be no real solution. Okay, so we want the quantity 2x minus 3 to represent a number that's greater than or equal to 0. Now, if I solve for x, I'd add 3 to both sides and then divide both sides by 2. And I get that x would have to be greater than or equal to 3/2 in order to keep that radicand positive or equal to 0. All right, so if that's the case, I could write my answer like this. That's set notation. Or if I want to write it in interval notation, I can write 3/2 to infinity, where we have a closed bracket here because we're including 3/2, and then infinity, we want to see that parenthesis. Here, arc sign. As soon as I see the word arc, I'm thinking to myself that I'm going to have one answer, and I'm going to need to pay close attention to the restrictions. Arc sign goes from negative pi over 2 to pi over 2. So I have to give my answer within that range. So let's go ahead and do our all students take calculus. You can see here that this sign value is negative. So sign would be negative in the third quadrant and the fourth quadrant. Okay, but remember, because of the arc, we're only working in this region, so I'm not going to use this triangle. So we're really just looking at the fourth quadrant here. Sine is opposite over hypotenuse. So if I take a look at my reference angle here, opposite of that reference angle is going to be radical 3, and the hypotenuse would be 2. Based on orientation, this would have to be a negative square root 3. And this is a 1 square root 3, 2 triangle. Okay. Now, because theta is across from the longer leg, theta is going to be equivalent to 60 degrees rather than 30 degrees. With arc problems, though, we want to write our answer in radian form. 60 degrees is the same thing as pi over 3. And normally, I would label this quadrant with, let's see, 5 pi over 3, right? But in this case, I do not want to put 5 pi over 3 as my answer. Because remember, my answer has to be in the range from negative pi over 2 to pi over 2. So instead of putting 5 pi over 3, I'm going to find a negative angle that's coterminal with it. And so I'm going to put negative pi over 3 as my answer. In part 3, we're doing a limit problem. Instantly, I can see that this is already reduced. I cannot factor it to reduce it any further. And you're going to see that we have an x minus 2 factor left in the denominator. That means we have a vertical asymptote at x equals 2. So notice I'm approaching 2, but I'm approaching 2 from the right-hand side. So as soon as I see that I'm approaching a VA, I know that my limit, my right-hand limit, is either infinity or negative infinity. So how am I going to figure that out? Well, if I'm approaching it from the right-hand side, let's look at a number that's a little bit bigger than 2. Like, let's look at the number maybe 2.01, something that's slightly bigger than 2. If I plug in 2.01, my numerator is positive and my denominator would be positive, and a positive divided by a positive would be a positive. So that means that my function is going to be going up to infinity from the right-hand side. Okay, and if we wanted to check our work, we could put that into our calculator as well. Let's go ahead and pull up Desmos. And I believe it was 3 over x minus 2. 3 over x minus 2. And we're looking at 2 from the right-hand side. So if I look at 2 from the right-hand side, you can see how it's going to be going up towards infinity on that right-hand side. That looks good. Okay, let's take a look over here now. Okay, for problem number 4, again, you can see that we're still approaching a vertical asymptote at x equals 2. So what is the limit as x approaches 2 if you're reaching a vertical asymptote? Well, the limit does not exist. That's what we're going to put as our final answer. If you didn't see that right off the bat, you would still run into a problem when you plugged in 2. See how you get 3 over 2 minus 2, which is 3 over 0. Because the value is undefined, that's why the limit does not exist. All right, let's go ahead and get into our new content now. For our example 1 today, it says find constants a and b such that the function is continuous over f. So what does the word continuous mean? That means no gaps, no holes, no asymptotes. Looking at the first problem here, we see a piecewise function. Now, where would this piecewise function possibly be discontinuous? If there was going to be discontinuity anywhere, it would be at x equals 2. See how that's where we make the jump from 3x squared to our linear function? Okay, so we want to guarantee that it is continuous at x equals 2. Like if I was going to plug in 2 into this first function here, 3 times 2 squared, that would really be 3 times 4, which is 12. I already know that I have a closed dot at 212. So if I'm thinking about the graph of this, at 212, I've got this closed dot up here, and we know it's a parabola, right? So I've got some kind of parabola going on when x is less than or equal to 2. Okay, now when x is greater than 2, there's going to be an open dot in this situation because it's not greater than or equal to, it's just greater than. So that's how I know to do the open dot. And I don't really know what this y value is going to be when I plug in 2 to my function because I've got this a value out front. Okay, and the whole idea of this lesson is we have to figure out what a is supposed to be to make this function continuous. So let me ask you a question. Would this function be continuous if we had an open dot at the point 0.25? Well, that would be some dot like this down here. See how there would be a gap in the graph? Would the function be continuous if there was an open dot at 2.7? Well, it's a little bit higher, but see, it's still a gap in the graph. What would y have to be in order for this to be a continuous function? Y would have to be 2, 12, because then I'd have an open dot overlapping that closed dot. Okay, and the closed dot takes priority. Okay, so if you have an open dot and a closed dot overlapping, you just count it as a closed dot. Okay, so that's what I need to see. So in other words, if I've got this function y equals ax minus 2, when I plug in 2 for x, so that it looks like this, y equals a times 2 minus 2. What do we want y to be? Well, we want y to be 12. So I'm going to plug in 12 for y. Okay, so now we're going to solve for a. We get 12 equals 2a minus 2. If I add 2 on both sides, we get 14 equals 2a. So a would be equal to 7. Okay, so rewriting this original function, we're going to have y equals 7x minus 2 would give us a continuous function. Okay, over here, let's just think about where this function could possibly be discontinuous. If I was going to think it's discontinuous anywhere, it would either be at -2 or 1, because you can see that at -2, we make the transition from the function y equals 3, which is a just horizontal line, to ax plus b, which is going to be some kind of linear graph, whether it's a positive or negative slope, I don't know. The other spot where it could be discontinuous would be at 1, because that's where I make the transition from my linear graph, either this or this, to another constant function, which is going to be a horizontal line through y equals -3. All right, so we've got our 2 spots we need to keep a close eye on. Let's go ahead and back up here and let's plug in -2 into the y equals 3 function. Really, it's just going to be 3 because there's nowhere to plug in -2. And I see less than or equal to, and that or equal to means it's a closed dot. Here we've got -2, and if I plug it in, that is a question mark. I don't know what the y output's going to be, but I do know that there's going to be an open dot there. And if I plug in 1, again, I don't know what my y output needs to be yet, but I do know that there's an open dot there. And last but not least, here if I plug in 1, there's nowhere to plug it in, so I know my output's just -3. And it's a closed dot because it's greater than or equal to. Let's just try to visualize this graph. I'm going to just put in some tick marks here. Okay, I first see that y equals 3 when x is less than or equal to -2. Because this is less than or equal to, I know there's going to be a closed dot at -2. Right, we'll have a point at -2, 3. So like this, and y will be 3 when x is less than or equal to -2. So you're going to have some graph that looks like that. Okay. I also know what this function is down here. This is another horizontal line, y equals -3, but we're only going to use that horizontal line when x is greater than or equal to 1. Again, I see that greater than or equal to sign, so I know there's a closed dot at 1, -3. Okay, so there's that, right? The y values are -3 when x is greater than or equal to 1. And the mystery is kind of what's going on here in the middle, because I don't know what A is and I don't know what B is. That's the whole question. I'm looking for constants A and B such that the function would be continuous. So if I wanted this function to be continuous, we're going to have to somehow connect these 2 points together. If I can't connect those 2 points together, then we're not going to get a continuous function. Okay, so that's what we need to keep in mind. So I know I'm going to have an open dot at -2 something, and I'm going to have an open dot at 1 something. Okay, and in order for this to be continuous, we're not going to want something like this. Like let's say I put -2, 5. See how the 3 and the 5 wouldn't match? Then I would have some point up here stacked on top. Okay, let's say that I had 1, 3 instead of 1, -3. If I had 1, 3, I'd have a closed dot there and my line would look like this. Does that give me continuity? No. What do we need to happen in order for this to be a continuous piecewise function? The y values are going to have to match, right? If this was 3, then this is going to have to be 3. For 1 down here, if that was -3, then this is going to have to be -3. Just think about it. We already have a closed dot at this point, -2, 3. So if I put an open dot over top of it, it's not going to make a difference. It's still overall going to be a closed dot. If I already have a closed dot at this point, 1, -3, right? We have a closed dot down here. If I go ahead and put this open dot, 1, -3 over it, it's not going to matter because it's still overall going to be a closed dot. Okay, so we want those y values to match up so that we get that continuity we're looking for. So let's come up with 2 different equations. Both of them are going to have to do with this y equals ax plus b. Because we have 2 variables to solve for, that's why we're having to write 2 different equations to help us find both of those variables. Okay, if I plug in -2 for x and 3 for y, instead of having y equals ax plus b, Now I'm going to have 3 equals a times negative 2 plus b. Simplifying that, we get 3 equals negative 2a plus b. Now let's go ahead and take a look at the second point, 1, negative 3, and imagine what that would look like to plug in 1, negative 3. Instead of y equals ax plus b, y would be negative 3 and x would be 1. Simplifying, we get negative 3 equals a plus b. Okay. So I have two equations, and now I'm going to create a systems of equations problem to help us solve for a and b. Right? Like if I put these together, I'd have 3 equals negative 2a plus b. Then we'd have negative 3 equals a plus b. Right now, if I add these together, we are not going to see a variable get eliminated. We would have negative a and 2b, and that's not going to help us. So I have to think to myself, what could I multiply one or both of those equations by to get a variable to drop out? Well, if I want to, let's say I'm trying to eliminate b. All I'm going to have to do is multiply one of these equations by negative 1. Let's go ahead and just do the top one in order to get b to drop out. Okay, so this is what I would have. This would become, let's see, negative 3 equals positive 2a minus b. And then the second equation, we're going to keep exactly the same. And now you can see if we add these together, we're going to end up getting negative 6 equals 3a, and the b's cancel. So I'm going to end up with negative 2 for a. Now I'm not quite done yet. I still have to get what b is equal to. So in order to do this, I'm going to plug into one of my original equations here. So either this one or this one, just to solve for the other variable. So let's go ahead and just do the purple. Let's do 3 equals negative 2a plus b. I'm going to plug in that a is negative 2. So we get 3 equals 4 plus b. And if I subtract 4 from both sides, we get that b is negative 1. Okay, so we just got the a and b values that would give us a continuous function. Okay, and remember the original form was y equals ax plus b. So the equation of that middle line, that linear function, would have to end up being y equals negative 2x minus 1. So let's see if that even makes sense with the graph. Well, if I look up here, it looks like it makes sense that our y-intercept would be at negative 1, and it looks kind of like the slope would be negative 2. So that makes sense. Another way we could have found that equation, negative 2x minus 1, and solved that the a value is negative 2 and the b value is negative 1, is I could have graphed it first, saw that this was the point negative 2, 3, and this was the point 1, negative 3, and found the equation by first getting the slope between those 2 points, and then secondly, use my point slope formula in order to get the equation of that line, right? And then I could identify what a would need to be and what b would need to be. Okay, just some food for thought. All right, the next topic here is intermediate value theorem. It says, if f is continuous on a closed interval from a to b, and w is any number between f of a and f of b, then there is at least one number, c, in that interval such that f of c is equal to w. So first of all, we need f to be continuous. So you're going to notice there's no holes, gaps, or asymptotes. And we have this closed interval, right? And these are both x values. You're thinking that a is an x value, and you're thinking that b is an x value. Okay, so we're going from the x value a to the x value b. And it tells us that w is a number in between f of a and f of b, which f of a and f of b are both y values. Do you see how f of a is a y value and f of b is a y value, and w somewhere in the middle, right? We have this y value, we have this y value, and w somewhere in the middle. If that's the case, if you have a y value that's in the middle, then that means that there must be some x value c on that interval. Okay, that's all we're saying. Okay, so let's take a look at example 2. Okay, so in example 2, it says verify the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. So first of all, I'm looking at a parabola, right, which is a continuous function on the interval from 0 to 6. So we're going to think about this like it's our a value and this like it's our b value, right? So we're going to start at an x value of 0 and we're going to go up to an x value of 6. And then it tells us that f of c is equal to 4. Okay, I'm going to first just start by rewriting my function in terms of c. So this is going to be c squared plus 4 times c minus 8. Okay, and I already know that f of c is equal to 4. So in order to verify that the intermediate value theorem applies, we need to make sure that 4 is in the middle of f of a and f of b. We need to make sure that 4 is a number that's in the middle of f of a and f of b. See how we're looking for a number between f of a and f of b? So let's just confirm that. Okay, f of a, remember, is just the same thing as f of 0 in this case. So what do you get if you plug in 0 into this function? You would end up with -8. All right, and f of b is the same thing as f of 6. Right, if I plugged in 6 into this function, what would I get? That would be 36 plus 24 minus 8, which is what? 52. All right, so I have confirmed that we can use the intermediate value theorem because 4 is between -8 and 52. Okay, so yes, the intermediate value theorem applies. Now the second part is I need to find the value of c guaranteed by the theorem. Well, really what 4 gives you is a y value. So the question is, what c value can I plug into my function to give me a y output of 4? Well, if I know that f of c is 4, I'm just going to replace f of c with 4 and solve for c. Right? How am I going to solve for c here? Well, I'll set this equal to 0 and factor it. Right? If I subtract the 4 on both sides, I end up with c squared plus 4c minus 12. We'll factor this. So we get c plus 6, c minus 2. Set each factor equal to 0. Okay, and solve for c. We end up with that c is -6 and c is +2. Both of those, if you plug them into your function, right, if you plug in 2 into your function, you'd get 4, and if you plugged in -6 into your function, you'd get 4, which is what we wanted, right? We wanted an f of c value of 4. But remember, the other condition that needed to be met was that our x values or our c values had to be on the interval from 0 to 6. So are both of these answers on the interval from 0 to 6? No, they're not, right? -6 is not between 0 and 6, so I would not put this one as part of my answer. So it's just c equals 2 because, let me make sure that looks like a because -6 is not in between 0 and 6. Okay, so it's just c equals 2 is our answer. Okay, let's try that again over here for part B. Again, we're going to start by verifying the intermediate value theorem applies. Okay, I'm going to rewrite this function in terms of c. So we'd have c squared plus 2 times c over c minus 1. Okay, remember we want the number 8 to be in between f of 3 and f of 10. Okay, so if I plug in 3, we'd get 3 squared plus 2 times 3 over 3 minus 1, which is what? 9 plus 6, which is 15 over 2. And then if I plug in 10, we'd get 10 squared minus 2 times 10 over 10 minus 1, which is what? 100 minus 20. And so that's 80 over 9. What does 80 over 9 reduce to? Nothing. It's just 80 over 9. Okay, so is 8, the question is 8 in between 15 over 2, which 15 over 2 is 7.5, and 80 over 9? which is about 8.8888 repeating. So yeah, the y value 8 is in between the y value 7.5 and 8.8. Okay, so here the intermediate value theorem does apply. So now I can go ahead and do my substitution. It tells me that f of c is equal to 8. So I'm going to go ahead and just plug in 8 for f of c. 8 equals c squared plus 2c all over c minus 1. Okay, and what am I going to do to solve this equation here? I'm going to go ahead and multiply both sides by c minus 1. Here the c minus 1's will cancel, and it'll leave me with 8 times c minus 1 equals c squared plus 2c. Okay, I'm going to distribute the 8 through to both terms. And we have another problem where we need to set it equal to 0 to factor. So if I subtract 8c on both sides, I would get c squared minus 6c. And then if I add 8 on both sides, I would get plus 8. Okay, so this would factor to be, let's see, maybe x or c minus 4 and then c minus 2. Set each factor equal to 0. Add 4 on both sides, add 2 on both sides. Okay, now one of those answers is not correct. Which answer would we have to exclude? 4 or 2? Well, if we're working on our interval, which is from 3 to 10, whoops. We're working on our interval from 3 to 10. The number 4 is between the x values 3 and 10, but 2 is not. So I'd have to exclude that from my answer. It's just going to end up being c equals 4. Okay. So 4 is the c value that I can plug into my equation that lies within this interval. That will give me a y output of 8. That's it. All right, let's go ahead and just talk through these examples down here. This is just completing the chart using always, sometimes, or never. Talking more about continuity. Okay, so we're going to start with a continuous function at x equals c. If a function is continuous at x equals c, tell me if these criteria are always, sometimes, or never true. If our function is continuous at x equals c, do we have a function output at the x value c? Is that are we going to have a closed dot somewhere? Yes. That's always going to be true if we're talking about a continuous function. What about the right-hand limit? Am I always, sometimes, or never going to have a right-hand limit? Always. There was a question on our one of our last note examples that said, do you always have right or left-hand limits? And we said yes. They said, are we always going to have an overall limit? And that was no. Okay, you're always going to have a right and left-hand limit. Okay, so right and left-hand limits are always. Is my overall limit going to exist if we're continuous at x equals c? Yes, always going to be true. Am I going to have a vertical asymptote at x equals c if it's continuous there? That's never going to be true, right? What about a hole? If we're talking about continuity, am I going to have a hole there? No. Continuous functions are never going to have a hole at x equals c. Okay. All right, now we're talking about removable discontinuity. Remember, think of an ice cream scooper where you're just scooping out one hole, right? Removable discontinuities, I want you to think of a hole. Okay. Am I going to have an f of c value with a removable discontinuity? Sometimes, very good, right? I can either have it where there's just the hole there, or if I want to, I could add in an extra dot, and now all of a sudden, now I do have an f of c value. So sometimes I will have an f of c value, sometimes I won't. It just depends on if I have a closed dot. What about a right and left hand limit? Always. You're always going to have a right and left hand limit. What about an overall limit? Well, if I approach from the left and right hand side and I just have a hole there, am I ever going to have an example where I don't have a limit? No, I'm always going to have a limit with a removable discontinuity. Okay. What about a vertical asymptote? For a removable discontinuity, where you're talking about an ice cream scooper, are you going to have a vertical asymptote there? No. Remember, removable is going to be just that little hole that's missing. All right, so this is obvious. Are you going to have a hole at x equals c? Yes. Okay. All right, non-removable discontinuity. This is where we have gaps in our graph or we have vertical asymptotes, right? That's non-removable. So am I going to have a functional value at a non-removable discontinuity? Sometimes, okay? So we can either have something that looks like this, right? Where here I would have a function value at x equals c, because see how my dot is closed in, right? Or I could have something where we have an asymptote, and I'm not going to have a function value at x equals c, right? So that's just sometimes. What about a right and left hand limit? I'm always going to have a right and left hand limit. Even if I have an asymptote, my left hand limit here would be negative infinity and my right hand limit would be positive infinity. Always going to have that. What about your overall limit? Am I going to have an overall limit if there's a gap or a hole, or I'm sorry, a gap or an asymptote in my graph? Am I going to have an overall limit if I have an asymptote? What's the limit going to be if you have an asymptote? Does not exist. What's your limit going to be if your right and left hand sides don't meet? Your left and right hand sides are different limits. Are you going to have an overall limit? No. So with gaps and asymptotes, this is going to be never. Okay? The limit does not exist if you have a non-removable discontinuity. Okay. What about a vertical asymptote for a non-removable? Is that going to be always or sometimes? Sometimes. Remember, non-removable can also represent gaps in your graph. Okay? It doesn't always have to be vertical asymptotes. That's only sometimes. What about a hole? Are you ever going to see holes in your graph? Do I have a hole in my graph here? When you have gaps or jumps in your graph, you are going to have a hole at one point, right, and a filled-in dot at the other. That's a possibility. Okay, so even though it's not a hole like a removable discontinuity where it's just scooped out, you still have holes. It just is associated with gaps in your graph, right? So I'm going to put sometimes because we're not going to have holes at vertical asymptotes, but we are going to have holes sometimes when you have gaps or jumps in your graph.